Now, even though we are using indirect methods to actually find the extrasolar planets, we can still figure out a lot about them. So each of the different methods actually helps us kind of understand different things about it. So we can actually determine the planet's orbital period, how long it takes to orbit, its orbital distance, how far away it is from the star, and the shape, the eccentricity of the orbit. We can determine the planet's mass and its radius, and if we have both mass and radius, we can figure out density, and if conditions are just right, we can even figure out atmospheric properties. Does it have an atmosphere, and what is that atmosphere made of? Now again, each of the different methods actually helps us figure out different properties. So all of the major detection methods, so again, this is the astrometric, the Doppler shift, and the transit method, all of these are able to help us determine the orbital period and the orbital distance. Okay, so how far away is the planet from the star, and how long does it take to orbit around the star? The astrometric and Doppler shift methods can also help us figure out the eccentricity of that. The transit method cannot. The astrometric and Doppler shift method can also help us determine the mass of the star. Remember, both the astrometric and Doppler shift, we're looking at how the star itself is wobbling, being pulled on gravitationally by that planet. So from that, we can actually start to figure out mass because we're looking at how gravity is pulling it. Now, something to note about the Doppler shift method is that it only gives us a lower limit. The problem is we don't know the inclination. We don't know how the star system is tipped compared to our own. Okay, so if it's exactly in line, then that's the exact mass that the planet has. But if it's away from exactly in line, then it's only a lower limit. It has at least this much mass, but it could actually be more. Now, the only method to tell us about the radius, the size of the planet, is the transit method. And we do that by looking at how deep the dip is. A larger planet is going to block more light, so the dip in brightness is going to be a lot larger. Now, to figure out density, we have to use two different methods. We take the mass as determined from the Doppler shift method, and then we look at the radius as determined from the transit method. So you can imagine, because we have to have the two methods working together, this isn't going to be as common, but it is doable and we have done it. So from these two, we can then figure out the mass divided by the volume, which is the density of the planet. Now, using the transit method, we may be able to get atmospheric information. So the idea is that we look at the spectrum of the star before a transit, so we know what the star looks like before. Then, when the planet crosses in front of the star, some of that starlight's going to go through that atmosphere and be absorbed. So we'll get new absorption lines. And so we can compare the spectrum before the transit to during the transit, and that can then reveal some of the atmospheric features. So using this, we've actually found atmospheres of hydrogen and helium, similar to Jovian planets. We have found some of these Jovians that also have signatures of water vapor, which is really exciting. I don't believe we've ever managed to do it on a terrestrial type planet yet, simply because they are so small, but we're right on the verge if we haven't actually done it recently. Now, we may also be able to determine the temperature of the planets during an eclipse. So remember, an eclipse is where the planet goes behind the star. So if the planet itself is really hot, it'll give off a lot of infrared light. So if we see the star and the planet both side by side, we add all of that light together and it's brighter. But when that planet goes behind the star, that infrared light is now blocked from our view and we see a dip in that light curve. Well, how big that dip in infrared is going to tell us the temperature of a planet. Now, in this case, the planet's going to have to be really, really hot to give off enough infrared that it's going to be easily identifiable compared to the planet, or compared to the star. But it is doable. In fact, just recently, meaning a few years ago, we actually found a planet that has a surface temperature hotter than the coolest stars, which is kind of incredible. All right, here is our fourth clicker question. Suppose you found a star with the same mass as the sun, moving back and forth with a period of 16 months. So it takes 16 months for it to wiggle back and forth. What can you conclude? A, it has a planet orbiting at less than 1 AU. B, it has a planet orbiting at greater than 1 AU. C, it has a planet orbiting at exactly 1 AU. Or D, it has a planet, but we do not have enough information to know its orbital distance. Go ahead and think about it, and we'll discuss in just a bit. All right, so we're looking at how the star is wiggling. So in this case, we're either looking at Doppler shift or maybe we're looking at astrometric. But the important piece is that it takes 16 months. So in our own solar system, with a star the same mass as the sun, which is the sun, it would, if we're looking at the Earth would cause the sun to wiggle back and forth in 12 months, right? It takes 1 year for the Earth to orbit around the sun. Okay, so, and the Earth is at 1 AU. Okay, now in this case, we're looking at a planet with a 16-month orbital period. Going back to Kepler's third law, the farther away the planet is from the star, the slower it goes. So this is a longer orbital period, so it's slower going around the star, which means that its orbit has to be greater than 1 AU. Okay, so the correct answer is B. It has a planet orbiting at greater than 1 AU. Now, this is pretty much exactly what we do in figuring out extrasolar planets. It's not some new weird mystery. What's amazing is the technology that has allowed us to pinpoint these things, but as far as actually figuring out orbital properties, it's all about going to Kepler's laws and Newton's laws that we've discussed previously.